Good afternoon, team. Hope I am audible. My audio is clear. Can anyone please confirm on the chat? Yeah. Okay, Motilal. Thank you. Thank you, Mallikarjunji. Sorry, Mallikarjun. Sorry for it. Yeah. So good afternoon, team. Thanks for your time, making your time for this session, a technical session on bare metal, collecting the profiling information from the bare metal application using Keil MDK. I believe many of the attendees who are part of this webinar is already well versed and aware of Keil. Maybe for some it may be a repetition, so please bear with me. Maybe for others who are new to them, it will be really a useful session. So basically, I had plan of playing this video, so I had put few slides of our company. Maybe I'll jump that quickly. I'll not go through them. So we'll start up. The agenda will be like, first we'll be discussing why anyone should go for debugging. Like everyone knows why the debugger is required, why user has to go for a debugging of the application, why at all it's required, and how the debug components. We're talking about basically this session will be on Cortex M, like doing the debugging on a Cortex M based processor, which is ARM v7M architecture. So we will be talking about what the various components of it and how they're connected, and later what is that debug technology which has been implemented in this ARM v7 architecture course, which was from ARM v7A, v7R, v7M architecture course. And later we'll be ending this session with a demonstration of collecting a profiling information from a running hardware or a code running on a target board or a hardware board, and in real time seeing the profiling information and the trace information. And I'll be having a time, maybe 15 to 20 minutes for FAQ, for any questions. If it's a basic question, please feel free to ask me. Let me introduce myself. I'm Geeta. I work here as a director ARM Tools in GSAS Microsystems Private Limited. We are the only authorized and prime distributors of ARM software solutions in India. And I have more than 2 decades of experience in ARM technology, and I've been handling this Keil software support part and everything. So any questions, please feel free to put in the chat window. At the end of the session, I'll certainly take that questions. So let's start with the session. Okay, so this was few slides of our company I had put. So let's jump to the software directly. So ARM Keil MDK development system. Basically, everyone knows what is an MDK. They know it. They tell someone pronounce it as Keil, some pronounce it as Keil, and that's the GUI and the software kit or a development system which helps the user to develop a code for any ARM-based microcontroller units. Please note the word I'm stressing, microcontroller units. The M stands for microcontroller development kit here. So ARM has wide range of processors from lower end to a higher end. So higher end, which goes to your smartphones, smart tablets, smart automation, home automation, smart city. So wherever the higher amount of data has to be processed and all, they use higher end device, which is Cortex A based. And we do have lower end, which is for Cortex M, which is a microcontroller, where the user wants to do some application which a microcontroller, it has to be done through a microcontroller. Then ARM also has given the processors based on Cortex M MCUs as well. So Keil software is the development system which helps you to develop the software for code for any ARM processor based MCUs. It is not only for Cortex M, it is from your legacy processors ARM7, ARM9, Cortex M0, M3, M4, M7, M23, M33, M35P, which is the latest one, processor core. So when we talk about ARM MDK development system, what does this comprises of? So it comprises of your MDK tools. It has ARM FUSA compiler. So when you develop, see, this particular software demo version is available for download from the Keil site, but it has a demo limitation of 32 KB. And when you download that software, you will be getting Microvision IDE and debugger with ARM FUSA compiler. I'll come to what it is. FUSA compiler at present, just take it as ARM compiler. Then you have software packs. With the demo version, you'll get the IDE compiler, debugger, which is the GUI debugger, and the pack installer. So what is the pack installer? With the help of pack installer, you can install the required software packs. So what are these software packs? Because you will be, you are developing a project based on a specific MCU, so device specific information, like when you're developing a software, it's like you have to program the peripherals of a microcontroller. So for that, what you do, we try to initialize those specific peripherals using the peripheral specific registers. And to access these registers, we need the device specific header file. So this software packs has first option device, you can see, is it gives you access to the device specific header file, which will allow you to do in the peripheral programming. And it also has flash programming algorithms. So the device what you have selected, if at all it has on-chip flash, then ARM has given many flash programming algorithms for each of the device that is being supported. But this flash programming algorithm has to be provided by the silicon vendor. When I tell silicon vendor, is the semiconductor vendor. For example, if the team is, if you're planning to use ST or an NXP or Atmel, which is microchip, or a Broadcom or any processor, the semiconductor vendor has to give the device specific files. That is header file, your flash programming files, if at all the device has the flash. And CMSIS is Cortex Microcontroller Software Interface Standard. So this particular is for specifically developed by ARM, a joint collaboration with ARM, semiconductor vendors, and the development tool vendors like Keil, IAR, or third party. So this particular CMC standard was developed for basically for Cortex M based MCUs. Later on, it was extended to few of the lower end Cortex A MCUs. Next, we have CMSIS. If anyone is interested, please go to developerarm.com. CMSIS will get a lot of information. CMSIS has various configurations. The default that comes with MDK demo is CMSIS DAP, CMSIS DSP, CMSIS RTOS. So CMSIS DAP is for debug access port. That is in this particular slide. So in this particular session, we'll be talking more about the debugging part. Though DSP, CMSIS DSP is for the processors which has with DSP unit. That is the Cortex M processor itself will have the DSP unit inbuilt with it. To name few, we have Cortex M4 based processor core, Cortex M7 based processor core, and Cortex M33 based processor cores comes with the DSP unit. So you're wondering what is this DSP? It's just a multiply and accumulate unit for doing the first arithmetic operations. Next, coming to MDK middleware. So MDK middleware is something everyone is aware what is a middleware is. If not, I'll just quickly tell what a middleware is. A middleware is one which sits between the application which is running on your hardware. It sits between the hardware and any operating system. Like suppose you have downloaded, if you have an hardware OS, hardware board, on that if you have ported any operating system, it can be Linux, Android, or it can be even a normal free RTOS or any microcontroller RTOS. So this middleware is sit between your application and the OS, basically. And this middleware is nothing but ARM gives the middleware stacks for the higher end communication peripherals. Higher end communication peripherals like USB host, device, networking, CAN, or you want to create a file system in the flash, system flash, onboard flash or external flash or RAM or external RAM. So for all those, has given a middleware stacks, and MDK middleware comes as part of it. Okay. Next, coming to debug probes, we have a wide range of debug probes from ARM. So lower end is Ulink 2, Ulink Plus, higher end is Ulink Pro. And today we'll be seeing the real-time profiling, capturing of the data from a running hardware board using Ulink Pro debugger. Okay. So Ulink Plus is basically a lower end of Ulink Pro version, but it helps in power analysis. To find out what is the overall power consumption of your application, Ulink Plus can be used. Ulink P was the very lower end debugger which ARM came up, and they started to give the JTAG debugger support. So any questions, please put in chat window. So quickly, I'll just take you through the various editions of Keil MDK. MDK software comes with 4 different editions. Now Lite is replaced with the community edition. Lite is nothing but the demo version. We have professional plus essential, and these are the various just differences between these editions. The higher end Keil MDK edition is professional, and the lower end is essential. The middle one is plus. So professional is a higher end version. It has all the features, like supports all the devices. It gives you access to the certified compiler, because ARM compiler is also safety certified or decertified by TUSUD to develop the code for a safety critical application. If at all your application or your product is going to a market which is safety critical, for example, automotive, railways, medical, or any industrial safety rules, that is ISC 61501. So this ARM compiler, certified version of ARM compiler, can be accessed with the higher end version of Keil MDK license, which is professional. With plus and essential, you don't have that option. Essential supports all Cortex-M based MCUs, plus supports the legacy ARM7, ARM9 along with the Cortex-M based MCU. And professional supports all the devices along with some additional features. Basically, it gives you the middleware stack for USB device, host, a network, CAN, and all. Okay, now just jumping directly to what the main topic of this session. The first 2 slides were just to give you a quick overview of what an MDK is. So now let's see basic debug requirements. So why should, I guess that attendees who has joined this session, they're aware why anyone should go for debug. So what does the word debug stands for? Debug stands for debug, removing the bugs from your application. What is a bug? See, when you're writing your code, it's just a simple code. Maybe you may not tend to write. You may not create any mistakes, or when I tell bugs, it's a logical error. It's not the syntax error. But if you're writing a million lines of code, it's for real-time application, which goes to a product, then as a human being, we tend to commit mistakes. So syntax error, everything you're doing, your ARM compiler will point you out and it will give you the error messages. And you can still correct it and you can rebuild the project. But logical errors, your compiler will not help you out. As a good programmer, we'll put a flow chart and then we'll develop our software code. But as a human being, we are prone to do mistakes, and we end up doing mistakes, some logic error, or maybe we write it correctly, maybe processor, sometimes maybe more data is initialized or more data memory occupied, stack may get corrupted. It can happen anything at the hardware level. Fine. So in that case, to figure out the logical errors of your application, we need to debug our code. So whenever there's a logical error and you don't have any debugging, you don't want to debug, or there is no debugging support for the processor or whatever the microcontroller are using, then there is no way of to do just trial and error method, try to replace some C statement, build the project, download the code to the board and see. But the higher end MCUs comes with something called as debug support. The debug support is being given in the processor itself, the processor core itself. It can be from lower end ARM processor core to higher end processor core. Even Cortex-A also, 64-bit core, 32-bit core. They all comes with the debug port. Okay, so what this debug port does? So basic debug requirements is any if you are looking for a debugger to help you in debugging your code and making it as bug free. Bug means don't take it as errors. Bug means usually it's a very heavy word. So bug here is just to see that there is no logical errors and your program works smoothly and flawlessly without any interruptions, without any hassles. So for a basic debugger, what do you require? You should be able to run control, that you should be able to single step through your code. Single step in the sense statement wise, one by one, statement wise, you should be able to execute the code. Second thing, to put a breakpoint on instructions. Like if you have written some if you have written 1,000 lines of code, you cannot keep on single stepping each C instruction. So for that, what we do, put a breakpoint on specific instruction, and we will put a breakpoint and we will stop the processor there. Until then, we will see after this processor stops at the breakpoint, with the help of a debugger, we'll be able to see what are the memory contents. Is the memory contents getting updated? Is my registers changing? Is my variables getting updated? So all this information you can find it out with a breakpoint. That is called as breakpoint. Next, with the debugger, we can also see the state control. State control means processor state. Processor state means ARM processor operates in various modes. Though Cortex-M is simple, only 2 modes. But if you go for higher end Cortex-A, Cortex-R, they operate in 6 to 7 exception modes. So processor state you'll be reading the registers, you'll be able to find out whether the processor is in a normal state of execution or is in the exception or an interrupt. Then with the debugger, you can also get the system state tag information. That is, with the help of debugger, you can directly modify the memory contents. We can access the system memory. We can see the peripheral registers. If you want, we can modify those registers. And with the debugger, you'll be able to, whatever code you have developed in Keil, you'll be able to download to the board. Either if the MCU has a flash, you can program to the flash. If there is no flash, then you have to load the code to the RAM. Either on chip RAM or off chip RAM, based on the size of the code. Then halt the system. With the help of the debugger, you should be able to do all this. And whenever required, you should be able to stop the processor, maybe by giving breakpoint or give a free run and then stop at a specific location. Then with the debugger, you should be able to see execution history. So execution history is something, maybe I'll talk about that in detail in the next coming slides. Execution history includes execution trace information. Means the debugger should sometimes be capable of giving you the trace or the history of the instructions, code instructions which are executed by processor. In the sense, what are all the code bytes the processor has executed by fetching it from the RAM or flash, whatever it is. Okay. So next, coming to what is the M3, M4 debug features. So before coming to Cortex-M debug features, let me talk about the traditional debugging mechanism which was implemented in the legacy ARM processor core, which is ARM7, ARM9, and all. So ARM7, ARM9, there was a debug logic implemented in the processor, but it was not a most advanced version like Cortex-M or Cortex-A, Cortex-R. It had some limitations. If at all you're loading the code to the flash, you can set up to only 2 breakpoints and with the help of the BKPT instruction only. But on the other hand, if you're loading code to the RAM, yes, you can set any unlimited number of breakpoints. And to see the memory location of the watch window, you have to stop the processor, put a breakpoint, stop the processor, and then view it. It's like stop, see and go, like stop, analyze and go, whatever. There was an embedded trace macro cell. We'll talk about ETM later, but ETM basically helps in capturing the execution history. Next, coming to debug features of Cortex-M3, M4. So the debug technology which was brought into Cortex-A, R, and M was called it as the core-side debug technology. So the core-side stands for core-site, means giving you the view into the core. So you may tell, Madam, ARM7, ARM9 also will give you view into core. True, but with Cortex-M, Cortex-A, Cortex-R, Cortex-M. ARM came up with a debug technology called as core site. So core site stands for your debug and trace. It's not just debugging. It's not just with the help of debugger. You'll be having a peek into your processor or peek into your application. You will be able to even trace. So trace, what is trace? We'll talk about that. Next slides. Coming slides. So M3, M4 debug features. These are the various blocks we have. Flash patch and breakpoints. As I told, in traditional, it was only 2 breakpoints, but here with the Cortex M3, M4, you can put 8 flash breakpoints. Or if you're using watch point, if you're using watch variables, there it will be 4 for flash and 4 for variables. And we have instrumentation trace macro cell. So we'll see what is that in the next slide. So these are the different debug blocks, and data watch point trace and instrumentation trace. These are the trace blocks. So what is, now we'll see what was the core site technology which was gone into M3, M4. So as I told in this first slide of Keil MDK, I told it comes with seems as DAP. DAP stands for debug access port. So what does DAP? If you bifurcate it, it will be DP, which is consists of debug access port is nothing but it consists of a debug port DP plus AHP access port, which is 8. Okay. So what is AHP access port? AHP access port is nothing but a block which is connected inside the inside this debug logic is implemented in Cortex and processor core to through the AHP bus or AHP light bus. AHP light bus is an internal bus of the ARM processor core, Cortex and processor core. Through this access AHP access port, as the name suggests, you can we can access the features of the processor, like processor, memory, peripherals, all those we can access it through this port, access port. And how through this access port you can access? Using this AHP bus, which is AHP light bus basically, and AHP light bus is again connected to the AHP bus. So that DAP stands for, of course, consists of debug port plus AHP access port. So debug port has 2 implementation options, which is serial wire JTAG debug port. It supports both 2-wire pin, because serial wire means you can debug your program only in 2 pins, like traditional JTAG. Though we place 20 pin, but only 5 signals of the JTAG pins are used. But here, for serial wire, you can only use 2 pins. The serial wire debugging support was implemented in Foresight technology. So it doesn't mean that a normal JTAG will not work. In the same JTAG pins, the serial wire pins is also multiplexed. So you can use both the way. But if you want a trace option, if you want to collect a trace, you have to configure the debug port as a trace. So this is serial wire or JTAG. So this will call it as SWJDP, which is serial wire JTAG debug port. And this is your AHP access port. Or it can be serial wire, which is serial wire debug port, or AHP AP. So not all the debug ports of the processors, ARM Cortex and processors can be configured as SWD or JTAG. This particular information will be there in your device-specific technical, device-specific user manual, based on that you can configure it. So if at all your device, you're configuring it as a JTAG only always, and you're not configuring it as serial wire, then there is no option. You will not be able to get any trace information. You will not be able to get any real-time profiling data out of it. To get the real-time profiling data out of it, you have to configure the debug port as serial wire. This is what it's written. Access port gets connected to the AHP light. It gets give you the access to the core, memory, and debug components. Okay, and next coming to debug access paths. So this is how the debug blocks are being connected inside a Cortex M3 Pro, M3 or M4 core processor. Maybe these debug blocks are present from the processors above Cortex M3. So if at all are looking for a debugging support or a trace support on M0 or M0 plus, it's very least. Maybe you can do the flash programming and single stepping. Your number of flash breakpoints is also reduced to 2 there. because it's a lower end Cortex-M processor. So here you can see this flash patch and breakpoint block, FPB, DWT, and ITM. All are connected to the AHP internal private peripheral bus. So this is actually connected to the AHP light bus, and to which you can connect to the Cortex-M core. Whereas your embedded trace macro cell, which is in different color, this is actually an optional and trace port interface unit, because all the trace which is created from the embedded trace macro cell goes to your TPIU as well. So these three blocks are actually connected to the external private peripheral bus. So because it's an optional, they're optional blocks. Whereas these three blocks you can see bold one, they will be present for any processors above Cortex M3 onwards. Okay. But whereas these two blocks is optional, and the silicon vendor or a semiconductor vendor who is coming up with a microcontroller will decide whether to put these blocks in their microcontroller. And these blocks are tied to the private peripheral bus, which is APB. So AHP is Advanced High Performance Bus, or those who know ARM architecture, maybe if there ever it is called as AMBA bus, Advanced Management Bus Architecture. Though this AMBA bus has a lot of revisions, now it is AXI3, AXI5, whatever. But this AHP is Advanced High Performance Bus. It's part of this AMBA bus only again. APB is Advanced Peripheral Bus. So AHP bus and APB bus both are different. So only it is shown separately, but both are internal to the ARM processor core. But the devices which are connected to the blocks which are connected to the APB may not operate at the same speed of the blocks connected to the AHP, because the any components or blocks which are connected to the AHP bus will be directly connected to the CPU core, and they operate at the same speed of that of the CPU. Any blocks which gets connected to the APB or external private peripheral bus, they may not operate at the same speed of processor, because there is a bridge in between. If you program that bridge, you can make this blocks operate at the same frequency of CPU, maybe half of it, 1/4 of it, 1/8 of it, basically to reduce the overall power consumption. So it's up to the silicon vendor to decide whether these blocks have to be included. And if at all the blocks are there and you want to use it in your application, then this AHP to APB bridge has to be programmed. So this is your serial wire or serial wire JTAG debug port, and we have AHP access port. So this together, two ports together becomes a DAC, debug access port. The JTAG debugger, which is a very ancient one, I should tell it's end of life by ARM, which was a real view eyes. Now it is replaced with a DCMST, or it can be a Keil debugger. So any questions, please, till now, please feel free to put it in the chat window. Okay. So I was telling about that ARM7, ARM9 debugging features and the limitations, and why at all ARM came up with a different debug technology in Cortex-A, R, and M. So there was some limitations in traditional way of debugging, that is run stop debugging. As I told in ARM7, ARM9, we have to stop the processor up to a specific point by putting a breakpoint and then see the status of the system. Okay. So this traditional way of debugging had some limitations. So ARM came up with a different debug core side technology, which will help the users address these limitations. So these are some of the scenarios where they have just explained why this run stop debugging, the traditional way of debugging, has a limitation or issues. So core site introduction, we talk about that in first slides. So as I told, it's a debug and trace technology in Cortex-M devices. Debug and trace technology basically here. It's suppose on-the-fly debugging. Because traditionally it was like stop the processor and then see the state and then execute. But here it is something, we can see the state of the system, state of the processor or your application without even stopping the processor. It is called as on-the-fly debugging. And what does this on-the-fly debugging do? When you're running the processor itself, we can set a breakpoint, we can modify the memory contents, we can change the variables, change the value of the variables. Yes, Shanmuga Priya, you have some question? Shanmuga Priya, if you have any questions, please put it in the chat window. I shall be able to take it up. You have raised the hand. Okay, thank you. Anything is there, please put it on the chat window. I'll come to that later. Okay. Then we have trace options. As it's a debug and trace, it's not only help with on-the-fly debugging, it also gives you the trace option. Trace, you have integrated data trace and we have optional instruction trace. So integrated data trace is the top 3 blocks which I showed you in the previous slide, where it is connected to the AHP bus directly. Optional instruction trace is one which gets connected to the advanced peripheral bus. And ETM is optional because this particular block occupies a lot of silicon place or a silicon place on the die. Lot of transistors it occupies on the silicon die, and thereby the device cost or microcontroller cost will be more if at all the semiconductor vendor like NXP, ST decide to put the ETM block. And in that, compared to the traditional way of debugging, we can debug your code in just 2 pins. So you are a debugger. And there is one additional pin is required if at all you want to see the data trace. So usually the data trace required as an on-chip trace. Okay. So this particular core side debug technology is supported in all the editions of Keil, Professional Plus and Essential, and the Uling family of adapters. So maybe the same thing, a bit elaborative way to show various debug blocks in Cortex-M processor, how they are interconnected, how the TPIO trace port interface unit is connected, all those. So run control is we can start the code, stop the code, single step through the application program. Breakpoint unit is actually, this is a here it is a merging of flash patch and breakpoint and data watch point. So totally 8 hardware breakpoints. So in the main hardware, hope the team is aware what is software breakpoint and the hardware breakpoint. So to quickly tell, hardware breakpoint is the one when you're setting the breakpoint in the flash. Okay, and when you're loading the code to the flash and you're executing the code from the flash, sort of breakpoints you set is the hardware breakpoint. Anything breakpoint, if you set it in the RAM, it is called a software breakpoint. So RAM usually it will be, memory will be more. So you can set unlimited number of breakpoints there. Memory access unit. Memory access unit helps the debugger to do the on-the-fly accessing of the memory. We can read the memory content, we can modify the memory content, we can write it even when the processor is running. Data watch point and trace unit, here we can put up to, actually this DWT has 4 analog comparators inside built, and any watch variable you add it to the watch window of the Keil, that specific variable address will be loaded onto these analog comparators. And whenever processor accesses this variable for reading or writing, that will emit a trace packet if at all the trace option is enabled. DWT, though it emits the trace packet, it will not generate the trace. It in turn triggers the instrumentation trace macro cell to generate the trace. Next block is your ETM trace. So ITM is the one which is triggered by the DWT, and this can also be used to see the printf information. What is printf information? So the traditional way of debugging still many companies follow, maybe not only startup, even the big companies follow, is they put a printf statements in between to see that the code is, to see whether the flow of the code is seamless, whether it is fine, whatever written the code, is it correct, the logic is correct. But an embedded engineer should realize that whenever you're using printf statement, it's like you're using one UART of the processor. So you have to initialize that specific UART, and then you'll be able to see the printf statements on the hyperterminal or any display, whatever it is. But dedicating a UART just for this printf information, like printf is what? It's just a kind of a debugging way, a traditional debugging way. Just we'll put some statements inside the printf just to ensure the processor is executing in a flow. But just for sending this printf or a debug related information, you're dedicating a UART continuously. Yeah, this may be true. It may be done with the microcontrollers which has 3 to 4 UARTs, though there are now microcontrollers in market which has 3 to 4 UARTs based on Cortex as a ARM processor core. But UART is very important in case you are using for any sensor related application or any wireless applications, basically for Bluetooth, Zigbee, anything, the data that comes to the processor is first converted to the serial or a UART. So UART is very much important. So ARM came up with a strategy, information or a kind of mechanism where they can route the printf statements, whatever printf statements. Yes, you can continue to use printf statements, but instead of routing the printf statement or whatever the string or whatever data you want to print, so routing it through UART, you can route it through ITM block, instrumentation trace macro cell, because it's a debug block. At the time of debugging only, this particular block will be useful for you. So if you're not debugging and you're running in a freestyle, like just programming the flash and powering it off, ITM is not even going to come to picture. So in that way, your purpose of debugging is also served and the UART is also safe. Next is ETM instruction trace optional, which is ETM stands for embedded trace macro cell, which gives you instruction trace. So what is instruction trace? Is ETM is a block which captures the information of all the code bytes or opcodes which are fetched and executed by the processor. So that is a block which captures all the execution history of the processor, and this execution history in turn will help us giving the real-time code execution analysis, profiling, and code coverage. So at the time of demonstration, we'll see how it is done. Then JTAG your debug interface. This can be 5-pin or traditional JTAG pin or a serial wire 2-pin. And if you want to see the on-chip trace, like if you want to use this printf related information through ITM, any trace packets coming from ITM, if you want to see, then you have to connect one more trace pin. And this trace pin is already part of the JTAG. So serial wire here you can see, because this particular one trace pin is a serial wire viewer. So you can see all the ITM and DWT related trace information. Okay. So here you can see all the trace coming from the ETM block, ITM block. DWT doesn't emit any trace. So trace coming from ITM and ETM block goes to trace port interface, and this trace port interface has a TPA, trace port analyzer, which will analyze and see the traces coming from which specific block. Is it coming from ETM block? Is it coming from ITM block? If it comes from ITM block, it will route the trace packet to through the serial wire viewer pin. It's additional one trace pin. If at all the trace is coming from ETM, then it routes to the Cortex debug plus ETM, which is actually a normal, it's not a normal debug port. It's a standard debug, it's the same debug port, but it has 5 additional ETM pin for trace pins. So you can see trace is written here, ETM, ITM not available on Cortex M0. So M0, M0 plus. M0 there is no trace feature at all, and M0 plus, yes, there is a trace feature where we can use this called as MTB, micro trace buffer, and some of the on-chip RAM of the processor itself is used to capture some trace information, but it will be very least, very negligible trace information. So if at all you are planning to correct the trace, then go for higher end Cortex device, which is M3, M4 onwards. So now coming to the trace connectors. This is a standard JTAG connector you might have seen on any hardware board. This is a 20-pin connector which has the pitch between the pins is 0.1 inch. You have 10-pin connector. This is also a JTAG port. It's not like this 20-pin JTAG, but the pitch between the two pins is 0.05 inch. And for Cortex, we usually use this for Cortex and Cortex debug. So it is called Cortex debug. So if at all you want to collect serial wire viewer trace from ITM or DWT, you can connect to JTAG or Cortex debug, but ensure these two ports you are configuring it as serial wire mode. Next is this Cortex debug plus ETM. You can see the pitch is still same 0.05 inch, but the number of pins is 20. Okay, and this is how this FRC cable which gets connected to this. It called it as Cortex debug plus ETM because additional 5 instruction, 5 ETM pins, 4 trace data and 1 trace clock pin comes to this for collection of the ETM trace. Because as I told, ETM captures all the opcodes processed or executed by the processor. So that specific data it sends to the debugger through this pins. A JTAG debugger like a Ulink Pro, Ulink 2 or a Ulink Plus can connect to this debug connector and can read that information coming from the ETM pin and store that trace information onto the system memory. On the system memory is your desktop computer or your laptop. But out of the 3 Ulink debuggers, Ulink Pro Plus and 2, Ulink Pro is the one which has intelligence or the firmware implemented which can read the data coming to this ETM port, ETM pins. Okay. So this is already I just have explained, discussed in detail. This is just a pictorial view of it. So you can directly modify the memory window, variables in the memory window. Then we have this printf style of information. This is an example which my colleague will run and show you at the end of this presentation in real time. So you can see here the ADC value through printf viewer. You are not using these printf statements. Is not routed through UART, but it is routed through debug log. This is trace records. You can see DWT plus ITM trace records. There is a trace records window. You can see in Keil debugger. So this will show all the information about PC sample, what was the instruction executed, any data that was read from a specific address and what was the data it was written or read. everything you can see this information, and this comes as part of the trace information. ITM again is the same thing here, but additional to debug printf, it can also show you the RTOS rated, it can also help you for RTOS server debugging. As I told, we also have CMSIS RTOS. So ARM has given the Keil RTX RTOS, which is part of CMSIS RTOS. And if at all you're developing your code based on RTOS, then you can also do this debugging to see what are the various tasks, what is the time taken for the execution of each task, task switching history, all those information you can get it through ITM. That is data trace again. ITM actually has 32 registers, 32 ITM channels, and each register is a 32-bit register. In that register 0 is specifically hardwired for printf information. So any printf rated data has to be routed through ITM, it will be routed through channel 0, and RTX rated RTOS server debugging information is routed through 31. So in addition to that, you also DWT also gives you exception and interrupt trace. So if at all in your code, if the processor is executing any exception or interrupts, it will also tell you the specific exception or the interrupt that was executed, how many times it was executed, time, minimum time, maximum time, all those information. Then we have logic analyzer. So with the data trace option, you can also get the logic analyzer. What is logic analyzer? Logic analyzer is basically used to monitor your variables graphically and to analyze your data. So this is how it shows logic analyzer, and you can analyze your code along with the logic analyzer at any point of time. If you place a cursor and click show code, then it shows the code, a part RC statement in the code which made this transition. So you can easily analyze your code along with this logic analyzer. So for this logic analyzer, we need a data trace. So wherever you see DWT, is all this information comes from your data trace. So wherever you see ETM, it's an optional ETM block which is embedded trace macro cell. So this gives you the instruction trace. This is how it shows. It can show you, as I told, when the processor is executing it, the ETM block just captures the opcode which is executed from the ETM port and dumps it to the system memory. And once you stop the processor, the Keil IDE will read that and it will display it in the readable format like this so that you can easily read it. So here you can see C and assembly. Here C and the equivalent assembly, so both you can see. So instruction trace helps you in analyzing the sporadic problems, incorrect timing, data corruption, all those information. So with the help of ETM, you also have a code coverage information. So what is code coverage? So code coverage is to see, ETM gives you what are all the opcodes or instructions executed. So code coverage will tell you in your C file, there are many functions. In each function, whether the function was completely executed or it was partially executed, you know why the processor executes some of the functions partially, because wherever there is a condition statement comes, like a if statement, for statement, while statement. So based on the condition, whichever is true, the processor takes that path. But it may drop the false path, in the sense, if the condition is false. It doesn't, the condition is true, it takes the true path, but false path is not covered. Maybe if the condition is false, then it will go to false path. Then the true path is not covered. So the code coverage will give you the information on how the processor has covered your code or executed your code. Why this information is required? See, as a part of IEC 61508, battery is dying. What is it? 10% batteries. Sorry for that, my battery is dying. So as part of IEC 61508, which is normal general safety standards, or it can be ISO 26262, which is for automotive. or it can be EN 50128, it is railways, or ISO 62301, which can be for medical. So for any safety standard, one particular safety standard in the sense, if you are developing a product which goes to any of these safety critical application, like railways, automotive industry, or medical, then you have to get your product certified by the certifying companies. So to get your product certified also, there is there are many things which your product has to undergo or has to certify or confirm as per the standards. So one such requirement is this software verification and validation. So with the help of code coverage, that is with the help of the trace collection from the ETM, real-time coverage, you will be able to get the code coverage, then thereby which will help you in getting the that particular part covered, which is software verification and validation. So maybe you may ask me, like, because code coverage is not complete, so you can see here some of the instructions. Maybe you can see here. Yeah. So some of the instructions you can see here, like clear records, it's only 16 instructions, 100% executed. Get line, only 12% of the 48 instructions executed, like that. So if you want to make this 12% as 100%, then we have to ensure processor takes all the path. If the condition is true, executes the true path. Then we have to modify the condition and make it as false so that the processor takes the false path. So all the paths has to be covered by the processor. So how do you modify this condition? We do it through unit testing. This is not the topic for this session. Testing information. Next, with the ETM, we can also get the real-time profiling information, that is performance analysis. The performance analysis basically tells what is the time taken by the processor in real time for the execution of a specific function in your program. Okay, so this particular performance analysis just tell me what is the time taken for the execution of a specific function, but it will never tell me in that particular function. There may be few statements where processor is spending the time unnecessarily. Maybe it's in some infinite loop or doing some delay or whatever it is. So to drill down to that information, we have execution profiling. Yeah, here it is. It's here only, execution profiling. So execution profiling is, again, it will tell you the time taken for every C statement or every assembly instruction. So this you'll get it as part of your real-time ETM trace collection. So what all you get? You get performance analysis, you get execution profiling, you get code coverage. So this is just now quickly to go through what are the adapters we have. I'll just quickly go through because my colleague has to even demonstrate the software. But actually the software, I mean, showing you the profiling application. So we have ULink 2, ULink Pro. ULink 2 is a lower end debugger. It doesn't have any support for instruction trace, but it supports the data trace on chip trace. ULink Pro supports data trace as well as instruction trace. It's a lower end debugger with ARM7 MCU on the board, where it has high speed FPGA. So the trace collection, what this collects and this collects, is this 100 times faster. Okay, this is just debug and trace features for this ULink Pro. It supports all ARM devices, ARM7, ARM9, Cortex-M. It supports serial wire debugger and it's attack debugging process debugging concept. It has instruction trace capture, the intelligence of capturing or reading the instruction trace via ETM. and it's supposed up to 50 megahertz data frequency and megabits per second memory read or write. So Ulink Pro helps in collecting the streaming trace. So streaming traces without stopping the processor. When you're running the code on the processor, ATM just captures the data, captures the opcode information, put it onto debug ATM. Ulink Pro reads that and puts it to the hard disk information. Hard disk is your system hard disk for a laptop. So this way you can collect your trace for a longer periods. Like if you want to keep your application or product for a burning test, burn means it's not putting a fire. It's like if you want to soak your application for a long time or to put for a burning test and see how the product functions for a longer period of duration. And in at any point of time, by mistake, accidentally or by unfortunately, if the product stops working, so this collection of trace for a longer periods will help you to eliminate such problem, detection and elimination of such problem. So Ulink Pro benefits, we have performance analysis, which is dynamic performance analyzer, which gives you the analysis of a running application. So thereby we can identify the bottlenecks. Because as I told you, we can be able to find out where the processor is spending maximum time, and thereby we can try to optimize that code. Because you are a writer, you are a developer of a program or a software, and you know where the processor has to actually spend the time, which part of the code is critical. Code coverage. This will actually help you to test your application and to ensure what are the code which has been executed. Execution history will help you to find the bugs or sporadic failures. Streaming trace, there is no trace buffer on the Ulink Pro. All the traces are directly being captured and dumped onto the system memory. So this will help you to analyze large sections of code and you can see the actual true behavior. So this brings me to the end of the session. And now over to my colleague Sonali. She has joined me recently, maybe a year ago, September. She helps me on all this demo part. Here she has joined as an FE and she'll be doing the demonstration and she'll be just showing the sample project, which is for the board. What we are using is Keil MCB 1760 board and that is based on NXP LPC 1760. Cortex M3 processor. Okay. So over to Sonali, and after Sonali completes her demonstration, I shall come to the question and answers. So let's stop sharing. Thank you, Gitama. Good afternoon, team. Once again. Yeah. Hope I'm audible. Okay. Let me, thanks, Mansingh and Motilal sir. Let me share my screen. So I'll be demonstrating a small example project from Keil only. And I am using the board LPC 1768 and with the Ulink debugger. Hope my screen is visible. So yeah, I am demonstrating a project based on MCB 1700, which is Blinky. And here, um, so
first we should in options for target in do debug tab. Here you need to choose the Ulink Pro debugger, and in settings here you can see the device, and the port is selected as SW, and in trace I have given the core clock as 100 and enabled trace, and I have also enabled the ETM trace. So okay, then I'll say in utilities I have enabled this use debug driver. Then I say okay. Let me build my project. So there is a 0 errors. Rebuild. Let me load my program to board, target board. So yeah, it is done. I have enabled debug. So here you can see my program has stopped in the main, and these are the register values. And when I run the program, here you can see the status. In trace status, that continuously displays status and progress messages. And let me reset and show you the breakpoint. And whenever I run, my program stops at this breakpoint. And let me show you how the single step works. So here you can see the single step one after the other. So next we have different trace features, and in component viewer that shows the detailed information about software components, and the event recorder that displays execution status and event information which help to analyze the operation of the software components. The system analyzer that graphically shows core clock, power consumption, interrupts, threads, and exception execution over the time. So coming to debug printf viewer for viewing, debugging, and program specific information. The performance analyzer view is used to view the execution statistics, the instruction trace for particular instruction with the time, and we have a event counters window that display the counter for each user selected event. So here you can see the trace data with the address, port, and the data. And here in call stack window, you can see the different variables with the execution type. And in coming to performance analyzer, here you can see the time taken for a particular module. And in logic analyzer, you can view the program in a graphical format. And here I have added the variable. So next we have a code coverage option in which you can see a different percentage the code has completed. So here you can see particular functions or modules, how many percentage or the execution percentage the time has taken. And this is the debug printf viewer. You can see. So let me disable this breakpoint. And here you can see the debug printf viewer, where you can see the AD values. And here you can see the trace exception with the total time taken and a minimum time required for a particular function or the module. So this is an event viewer which shows the time for a particular event. So here you can see the starting date and starting time and the beginning time, and the current duration it has taken. So here you also can change the register values, and by single step in you can see excuse me, the changes. So here you can see 100% of 37 instruction in ADC, the code coverage percentage. Here you can see the starting and ending time of the particular event. For main, it has taken a duration of 12.75 microseconds. And coming to logic analyzer, you can view the program in a graphical format. So here you can see the changes for a particular variable AD underscore done and the AD underscore DBG. It's changing, and you can also zoom in and zoom out. Here you can add a particular expression to know the value and which is the type of the variable. Yeah. If you have any queries, please put that up in a chat so that we can answer it. Yeah. Thank you.
Yeah. Thanks, Sonali. Thanks, Sonali, for the demonstration. Hope the team is clear. And If anyone wants to put a question in the chat window, please feel free to put. I have a few questions. Let me take them. First question from Mansingh. Can we debug an ISR? Yes, we can debug an interrupt service routine. So how do you do that? Because ISR is also a function, but until processor, it's like a normal, it's not like a normal function, like until you call the function in your program, it will be executed by the processor, but ISR is something which as soon as the interrupt comes and the interrupt is enabled in the processor or NVIC, Natural Vector Interrupt Controller, or any ARM processor, then the processor goes to ISR, interrupt service routine, provided the address everything is being given in the interrupt vector table, which is part of the startup code, Keil startup code. So if you put a breakpoint in ISR, starting C statement of the ISR, and you run the processor, once the interrupt triggers, the processor will come there, and if at all you enable the interrupt everything and given the interrupt handler address everything in the vector table, the processor has to come to your ISR, and thereby you can, from there you can put single step and everything, you can debug your code. Chakri, how can we set required data in the stack memory from one address range to next address range in debugger? Chakri, first of all, this question, I really don't understand the reason of asking this question, because stack is handled directly by the processor. We don't meddle with the stack, and stack is very important in your embedded project, and based on any nesting of the functions or any interrupts or exceptions, the state of the application or the state of the processor is pushed onto the stack. So so my suggestion is don't meddle with the stack. If you want, you can modify the memory locations, other RAM locations in the debugger. Is there any command in Keil to set memory range with my data? Yes. If you go to share my screen. Let me launch Keil. So here in the books, we have complete user's guide or MDK. So here, if you go to Microvision user's guide debugging commands, we have something called as memory set. Just checking memory set. You have a command called as memory set, where we can set a specific range, starting address, end address, and fill up with the data. Just looking for it. What sets? No. See, this is the, it's not a command, it's actually a function. So you can write this function, like you may ask, this is part of the C function. It's not part of your main application. They are just given as a debug function to help you in debugging the code. So this you can write it in a separate file and name it as .ini file extension and give it that here. Give the path of that ini file here. And as soon as you enter the debugger or simulator, it should be the ID will execute that and it will fill the specific start address and length and with the value. Okay. So is there any function to give stack memory details? Motilal, there is no stack memory details, but you can see the stack in the debugger where you see the watch window. Where my colleague showed, maybe but I missed it. There is a stack option there. You can see it by default. There is, you need not enable that. Whatever is the contents of the stack, you can see that. Yes, we can get code coverage for assembly also. So even if in your program you have written assembly, whatever is the assembly instructions the processor has executed, you can see the code coverage of that as well. Can you show an example of debug printf on Cortex M0 plus MCU? See, to show an example of debug printer for Cortex M0 plus, as I told, there is no trace block in Ravikashi. There is no trace blocks in M0 at all. M0 plus case, it has micro trace buffer, but that is very least, and we don't have the board with for Cortex M0 plus to show you the debug printf information. Okay. We have only this port from Keil. But in fact, we don't have any M0 plus voice ports to show you this feature. So any other questions? 2 minutes. Any questions, please feel free. Does debug printf work in simulator? No. Debug printf is actually with your hardware. Yeah, could be virtual serial port. See, what do you mean by virtual serial port here? If you want, you can see the printf information in simulation because there is no hardware and there is no problem or danger of using the UART there because it's virtual simulation and there is no hardware in it, and you can see printf information in the simulator. That's possible. Virtual serial port. Any example? Let me check. I guess it should be done. There. No serial, I guess. Now I'm running the code in simulation. Serial. Yeah. 0. So we'll go to view, serial window, UART1. It's here, UART1. Can see ADC printf implemented. Just a second. LPC 812. LPC 812, I guess LPC 800 is a 51 base processor. 812. What is 0? We don't have sample application. I'm just trying to show you here. You can see. Do you see here ADC value printed? Or maybe we can see that by putting a breakpoint here. ADC is triggered. And you are seeing ADC is already started printing. So it does print the printf statement, but we don't have any example program for Cortex M0 and LPC 812 processor based. If any application board is there, development board is there, and if Keil has given support for that board, because development board manufacturers will approach ARM and they'll request to include the example projects, and there we can see it. If at all the development tool manufacturer or vendor has given development board, rather, if they given any printf related sample project, then we can see it. So this I'm trying to implement. So you can see here it's 926 ADC. This is the printf information. You can see this is the virtual simulation. A simulator. You can see the virtual serial port, and serial port data that is coming to the serial port of the processor you want. Okay. So, any other questions? Thank you so much, team. If you still have any questions, you could not ask me here. You can send it to GSAS mspl.com, git@gsasmspl.com. This is my mail ID. So please feel free to send any questions you have, or if any of you are looking for licenses or software, any sort of consultancy, like if you consultancy in the sense like you want to know which particular processor is suitable or whatever it is, then you can please feel free to send me an email. Actually look into it. And thanks once again for the team for making your time in attending this webinar. Hope the webinar was useful. And I'll be conducting technical webinars every month. So next month I'll come with one more technical webinar. Thank you. Thank you once again. Wish you all happy Dasra. Those who are part of South Indian, those who are part of North Indian, it is happy Navratri. Thank you all.